Hi, I'm Ziheng Chen. I'm here to present our CVPR paper, Hyperbolic Busemann Neural Network. So in this work, we introduce a new framework by Busemann function to build the hyperbolic neural network. So the hyperbolic space, which is a non-negative curved manifolds, it has shown power in tasks which have hierarchical structures. So previous work have shown that they can do deep learning things on such space for hierarchical task. The basic thing is to how to do deep learning over this non-Euclidean space. We cannot use the Euclidean networks. We should have a hyperbolic version of networks. So we use the ideas from the metric geometry called Busemann function and its level set. So here is the definition. And the interesting thing is that the Busemann function generalizes the inner product, which is shown here. So in Euclidean space, it is reduced to the inner product. And secondly, we have the closed form expression for the Busemann function for over hyperbolic space, such as Poincare ball and the Lorentz space. And this table summarizes how Busemann function generalizes the Euclidean things. So an interesting finding that in Euclidean network, there are many layers or basic units are based on the inner product or hyperplane. So which means that we can use the Busemann function and the holosphere to do deep learning over hyperbolic space. So first we focus on the classifier, which is called the Euclidean multinomial logistic regression, or more familiarly, it is composed of the fully connected layer and the softmax. And if we write it elementally, we can find the inner product inside the formulation. So which means that we can use the Busemann function to replace the inner product and then get the Busemann MLR. Another interesting thing is that the Euclidean MLR can be interpreted by the point to hyperplane distance. And parallelly or similarly, the Busemann MLR can be interpreted by the point to holosphere distance. And we can find the point to holosphere distance and also the final expression share the similar expression with Euclidean things. So here is the two things, how our BMLR generates the Euclidean MLR. And the next thing is to do the FC layer. To do the fully connected layer, we find that the right-hand side is just similar as the MLR. We just need to solve the left-hand side. And the left-hand side is equal to a certain point to hyperplane distance. And to do it in the hyperbolic space, we only need to solve the point to hyperplane distance and put the Busemann function in the right-hand side. So this is how we get the hyperbolic version of Busemann fully connected layer. And in the paper, we also consider the activation and the biasing parameter and the biasing. So these two tables compare our Busemann MLR and the Busemann FC with previous hyperbolic version layers. We find that our layers have several merits such as compact parameters, batch efficiencies, or comparable complexities. And we did experiments on different tasks. So the first set of tasks is to verify our MLR. We compare with the previous hyperbolic MLR on different kind of tasks. The first is image classification, and the second is general sequence learning, and third is graph learning. We can find that our MLR has shown better performance than the previous hyperbolic MLR. And the second set of experiments is for verifying our fully connected layer. We compare our Busemann FC layer with previous FC layer. Also, in most of the case, our Busemann function shown better performance. So that's all. Thanks.